Hello everyone, my name is Vivek and my roll number is 19951821997, studying in 6th semester in Aeronautical Engineering Department. Today, in the subject of computational aerodynamics, the Tech Talk topic is about application of system identification to high performance aircraft. A concept of system identification applied to high performance aircraft is introduced by a discussion of the identification methodology. This methodology includes 5 steps: model postulation, design of an aircraft, data of compatibility analysis, model structure determination, and parameter estimation combined with data collinearity diagnostics and model validation. Special emphasis is given to optimal input design and model structure determination, data collinearity detection and assessment, and biased estimation technique suitable for the analysis of high collinearity data. The process of system identification has been applied to aircraft for over 20 years. During these years, several different approaches and methods for uh, aircraft model structure determines and parameter estimation from flight data have been proposed and tested. Because the formulation of the aircraft dynamics is based on known rigid body equations of motion, the unknown structures and parameters are related to aerodynamic forces and moments acting on the aircraft. Estimation of aerodynamic parameters from flight data has become almost a standard procedure for augmented aircraft and in-flight conditions where the aerodynamic characters can be described in linear terms only and when no significant external disturbances are present. However, the introduction of highly maneuverable and often inherently unstable aircraft has been presenting new challenges to aircraft identification and parameter estimation. These aircraft can perform rapid, large amplitude maneuvers, often extended to stall and post-stall regions where nonlinear and unsteady aerodynamic effects should be pronounced. This produces, see, sorry, this introduces a problem of determining how complex the model should be. Although a more complex model can be justified for more accurate description of airplane motion, if estimates for too many parameters are sought from a limited amount of data, a reduced accuracy can be expected or limited of failure. The high performance aircraft may also have many control surface movement through a flight control system than conventional aircraft. Such a system can introduce relationship between the deflection of various surfaces and at the same time can preclude maneuvers from being suitable for system identification. A successful parameter estimation requires the following: design of an air experiment for obtaining data with high accuracy, high information content, and low collinearity among measured inputs and outputs, determination of model structure which represents an adequate model for the aircraft under test in each maneuver analyzed. When severe data collinearity could be avoided by experiment design and introduction of techniques which reduce the adverse effect of data collinearity on parameter estimates. So this is the basic block diagram of the high performance system. The aircraft identification methodology. When aircraft identify when system identification is applied to an conditions governing its motions are postulated and an experiment is designed and for obtaining the time histories. So the equations of motion are formed by rigid body force and momentum equations and by a set of kinematic equations relating the Euler angles and angular velocity. M v dot plus m omega dot into velocity is equal to f of theta into v omega and u, where and I omega plus omega into I omega is equal to g of theta into v omega and u. In equation where m is the mass, I is the inertial matrix, v and theta are the linear and angular velocity vectors and u is the control velocity. The vectors f theta and g theta represent external forces and moments respectively, and theta is a vector of parameters which specify aerodynamic characteristics of the aircraft. For system identification, the aircraft state equations are completed by output and measurement equations. The complete set of all the above equations can be written in a concise form as x dot is equal to, in this form, where the state vector x is comprised of v, uh, the omega and Euler angles, and the control vector of control surface deflections. The outputs y are the variables defining aircraft responses. The measured outputs z of I are corrupted by measurement noise, and the number of data points is n. Aircraft identification can be stated as follows. Aircraft identification is a determination from input and outputs of a structure of f theta and g theta and unknown parameters theta in f theta and g theta. In many practical applications, the structure of f theta and g theta is assumed to be known, and aircraft identification is reduced to parameter estimation. A general approach to aircraft identification adopted at NASA Langley Research is shown in the figure in the form of block diagram. This is of various steps, including procedure, include model postulation, design of an experiment, data computation, compatibility analysis, model structure, determination of parameter. So this is the basic block diagram, which is from the model postulation to the design of experiment, and then with the measured data to the data compatibility analysis, and then we get the data. So model postulation is influenced by selected type of maneuver intended for system identification and by prior knowledge about aircraft aerodynamics. The aircraft aerodynamic forces and moments are expressed in the form of polynomials. This CA is equal to theta naught plus sigma of j is equal to 1 to n minus 1 theta j xj, where CA is aerodynamic coefficient, theta naught and theta j are the parameters, and the xj now represents input and output variables. So the design of experiment. Design of experiment involves a variety of activities, including selection of instrumentation system and specifications of the aircraft configuration, flight conditions, and maneuverability for system condition. Data compatibility analysis. In practice, often the measured response data, even after careful handling, can still contain bias errors. In order to verify data accuracy, a compatibility check can be applied to measure aircraft responses. So the model equation for the compatibility analysis are as given below. So the state equations are formed by kinematic relationship and the parameter vector, usually containing constant offset and scale factor errors. The estimation techniques are similar to those used in estimation of stage and aerodynamic parameters. The other one is the model validation. The model validation is the last step in the identification process and should be applied regardless of the complexity of the estimation methods. The resulting model must demonstrate that its parameters have the physically reasonable values and acceptable accuracy. So with the optimal input design, we intend to the advent of high performance and highly augmented, which has been more difficult to find the proper inputs, and through this formula we go through this design and we get the flight data which is more accurate. So the characteristics and the procedures in the optimization are multiple input design capability, practical input constraints, output amplitude constraints, global minimization of the cost. So the concluding remarks are that system identification can be applied for aircraft, has proven to be a powerful tool for aircraft modeling based on experimental data. In recent years, the introduction of highly maneuverable augmented technologies with high sophistication in aircraft identification methodology. At present, this methodology includes 5 steps as discussed, and the new technique for input optimization embodies several capabilities for its practical application. Experimental data are first checked for any uncorrected bias errors, and then after necessary corrections used in model structure determinations and parameter estimation constraints. So this is the flow through which the control surfaces has been generated in which is the rudder and the aileron, and this is the another block diagram of the data. And by this I come to the end of the topic. Thank you.